Hello and welcome to today's IALD webinar, Lighting Design and GUV Technology. My name is Joe DeGuzman from the IALD and I'll be your host for today's webinar. Let me introduce you to our panelists. First, Dr. Bob Karlasek, Jr. is the Director of the Center of Lighting Enabled Systems and Applications, LESA, at the Rensselaer Polytechnic Institute. Dave Fund is the President of Tambient at the Lighting Quotient. Darcy Chinnis is an ILD professional member and associate principal at HLB Lighting Design. We want to thank our sponsor today, the Lighting Quotient, for supporting this webinar. The Lighting Quotient's Tambient, a leader in task and ambient lighting solutions, offers unique UV-C technology for destroying viruses, germs, bacteria targeted to work surfaces, including desks, benches, conference room tables, private offices, laboratories, and more. Lighting at work. With that, Bob, take it away.
Well, thank you very much. And I'd like to thank the IALD for having me participate in this webinar and give a researcher's overview of some of the UV basics that go into all the concerns that people have now about how to incorporate UV systems in lighting design in the built environment. And one of the things I'd like to do is start with some UV basics. Shown on this slide is just kind of a bread and butter sketch of what we have in terms of the ultraviolet spectrum. Of course, the ultraviolet spectrum, as you see on the lower left-hand side of the slide, is a continuum of electromagnetic radiation that goes all the way from radio waves out to gamma waves. And the wavelength, usually measured in meters for radio waves and all the way into fractions of a nanometer for gamma rays, is a measure of the electromagnetic spectrum energy. The shorter the wavelength, the higher the energy. Now, all electromagnetic radiation interacts with matter. And in the UV region, this radiation gradually becomes energetic enough to cause molecular damage to some materials. The electric field can actually start to tear apart molecules. Now, in the top left is a table showing how UV radiation is typically divided up into different spectral regions, depending upon the energy or the wavelength of the individual UV bands. Outdoors, we are exposed to UVA and UVB radiation in sunlight. But fortunately for us, and for most living organisms on the planets, including plants, UVC radiation from the sun is absorbed by the ionosphere and doesn't make it down to the Earth's surface. So in normal life, no one on the surface of the Earth is exposed to UVC or vacuum UV radiation. Now, vacuum UV radiation is also absorbed in the ionosphere, and it's also absorbed by air as well. It does not transmit through oxygen and nitrogen in the atmosphere, so it only transmits in the vacuum. Now, if it weren't for the ionosphere blocking UVC radiation, life as we know it here on Earth probably would not have developed like the way we have it today. Now, let's take a look at some of the molecular reasons for why UVC radiation is regarded as germicidal, and the lesser role in germicidal action for the UVA, UVB portions of the UV spectrum. So if we take a look at the next slide, we'll see that the UVC spectrum is at the top of the blue bar, purple bar on the left-hand side. Below that is UVB and UVA. Now, this is a complicated slide because the way in which light interacts with matter is relatively complicated. Let's focus on what UVC does first, and the dashed purple line between the boundary of UVB and UVC is kind of showing where the energetic UVC radiation interacts with the DNA in our systems. Let me just do something here. So on the top right, you can see what happens when UVC energy is absorbed by the DNA or the RNA. The radiation is actually energetic enough to break the bonds of the DNA or RNA. Those bonds promptly loop into dimers, rendering the DNA unable to reproduce properly. This essentially disables the microbe or the virus from reproducing. Really, you need to be in the UVC band to quickly disable the DNA from functioning in a microbe or in a fungus or in a virus. And it really is a very quick acting process, completely disabling or disinfecting those particular microbes. Now, below that dotted line, UVB, UVA, and even to a degree 405 nanometer radiation can still be germicidal, but typically only when it's chemically assisted by being absorbed by molecules that generate reactive oxygen species. So it's a process that is much more complex than direct UVC deactivation. Now, a microbe, because typically is going to be disinfected using this lower process, because microbes and just about any full cell will contain molecules like this porphyrin molecule shown on the lower right-hand side that will absorb these UVB, UVA, and 405 nanometer wavelengths to generate reactive oxygen species. And then those reactive oxygen species diffuse around and destroy elements of the microbe. And that's why they're germicidal. So it's a concerted mechanism. It tends to be much more slow. And meanwhile, UVC is a direct bond breaking mechanism. It's fast and effective. Now, all ROS mediated processes are typically not worth considering for viruses, because unless the virus is in a very special environment, there are no reactive oxygen generating chemicals around to absorb the light and generate reactive oxygen species to attack the virus. So for all intents and purposes, UVB, UVA, and 405 are not really worthwhile to consider for virus disinfection, but they can work well, albeit slowly, for bacteria and similar kinds of cellular pathogens. Now let's take a look more closely at UVC wavelengths and dose considerations for germicidal systems. So what you see on this slide is something called a germicidal action curve. Now, germicidal action curves have been generated since the 1930s because people have recognized that UVC radiation has been useful for germicidal activity since the turn of the last century in the late 1890s and early 1900s. Now, note two things that are important about these germicidal action curves. First of all, the wavelength makes a difference, with the most studied wavelengths typically being below about 200 nanometers. Note that below 300 nanometers, or at wavelengths longer than 300 nanometers, there's very limited effectiveness on the germicidal action spectrum for basically disinfecting microbes of any kind. Second, you'll note that the dose needed to deactivate a pathogen depends upon the pathogen, and the overall shape of the curve between about 250 nanometers and 280 nanometers is about the same for just about all viral and bacterial pathogens. The only difference that is required is the dose and the specific wavelength that's involved. Now let's unpack dose. Typically, we measure UV irradiance in watts per meter squared. We can get the dose, or UV irradiance in watts per meter squared. We get the dose, which is the UV energy required by multiplying the irradiance times the exposure time in seconds. Now, most of the world specifies dose, a measure of energy per meter squared, but in the US, it's more common to use millijoules per centimeter squared. And you can see here that 10 joules per meter squared is about 1 millijoule per centimeter squared. Now, the takeaway from these germicidal action curves is that UVC radiation, if it can reach the DNA, will always deactivate the microbe or the virus. It always works, provided a high enough dose is delivered to the DNA or the RNA. UVC radiation will kill any pathogen, whether it's a virus, whether it's COVID-19, the so-called SARS-CoV-2 virus, so long as the dose is delivered. Now, the delivered is the key word. UVC disinfection is line of sight. If the microbes or virus are out of sight of the UVC radiation, they won't be impacted. Also, if the virus or the microbes exist in a droplet floating around in the air or inside of some kind of a chemical material on a surface, a higher dose will be required because that UVC radiation will need to penetrate through the liquid around the virus or the microbe to be able to get to the DNA. But if the dose is high enough and delivered to the DNA or RNA, it will kill pretty much any pathogen that is around. Now, remember that UVC radiation is energetic enough to break the chemical bonds of DNA. You might ask, what does it do to other materials when UVC radiation is used in the built environment? Shown on this next slide is the way in which materials commonly used in buildings will behave in the presence of UVC radiation. Now, building systems use many of these materials, and if you use UVC radiation for extended periods of time to disinfect surfaces, you will likely damage many of these kinds of materials in the built environment. Now, you've all experienced this even with sunlight, where sunlight will bleach out colors and damage some materials after low exposure. And that's only with UVA and UVB radiation. UVC radiation is much more energetic and can cause damage in these materials even faster. Now, some of the materials in this particular chart that exhibit moderate or high degrees of damage upon UVC radiation exposure are commonly used in carpeting, furniture, and as additives in some paints and varnishes for furniture. And unfortunately, the long-term effect of UVC exposure to common paints, furniture coverings, and carpetings are not well studied. And this needs to be considered if UVC systems of any type become commonplace in the built environment. There may be chemical solutions that make building materials more resistant to UVC irradiation, but more study will be needed. As a general rule of thumb is that the higher the dose and the shorter the wavelength, the greater the degree of damage to the surface of many common building materials and fabrics. Now, let's talk a little bit about some of the types of devices that are used to generate UVC radiation. Of course, the time-honored source of UVC radiation is the UVC mercury lamp. It was developed well over 100 years ago and broadly commercialized in the 1930s. It's the lowest cost, most efficient UV source available today. Note that some UVC lamps can be made to emit at wavelengths below 200 nanometers. Specifically, the mercury lamp can emit, if built according to a certain protocol, radiation in the vacuum UV that can be used to produce ozone. Of course, for most germicidal applications, we don't want ozone being made, so it's important when specifying a mercury lamp to make sure that it's made of quartz materials that don't transmit vacuum UV radiation and thereby make it impossible for it to really generate ozone. I've heard some complaints from people making homemade systems that they smell ozone when they turn on their mercury lamps. But a properly designed system will be extremely effective as a germicidal UV producer, but not generate any ozone. A couple of other points is that while the efficiency is quite good, the lifetime of UVC mercury lamps is limited. And while the lifetime is typically specified as being between 10,000 and 15,000 hours, that lifetime is only realized if you manage the temperature of the lamp appropriately and if it's left on continuously. Generally speaking, mercury lamps don't like to be turned on and off, and if they're turned on and off frequently, their lifetime will be less. However, because of their cost and efficiency, mercury lamps will continue to be used for germicidal applications for quite some time. Now, as lighting designers, you're probably familiar with the fact that LEDs killed off a lot of fluorescent lighting products in the lighting space. Now, UVC LEDs are commercially available and getting lots of attention. So let's look at UVC LEDs next. In the case of UVC LEDs, We have made a lot of progress as LED manufacturers in designing better devices. They've been around for about 20 years, but they are much harder to make than the blue LEDs used for solid-state lighting systems, and they're still generally at a much earlier stage of development. For a lot of reasons, the efficiency of UVC LEDs remains quite low, though progress is gradually being made. Most UVC LEDs have peak emission wavelengths between 250 and 280 nanometers, making them useful for germicidal activity. Basically, the wavelength produced, just like wavelengths of LEDs in the visible region, depends on the target wavelength of the LED manufacturer. Now, it's important to note a couple of things about UVC LEDs. The efficiency, though gradually getting better, is still quite low relative to lighting LEDs, typically around 7% or so. Second, the shorter the LED wavelength, the less efficient it is. So as you go from 280 nanometer UVC LEDs down to 250 nanometer UVC LEDs, the efficiency drops rather quickly. Now, just like all LEDs, designers using LEDs, UVC LEDs in germicidal systems will need to worry about UVC binning and lifetime when designing a UVC LED germicidal system. Another big difference between UVC LEDs and their blue LED cousins is that the lifetime of UVC LEDs is considerably less, with L70s typically less than 10,000 hours. That will need to be factored into the design of lighting systems that have a UVC component, because the UVC LEDs will just simply not last as long as the solid-state lighting LEDs will for general illumination. Finally, it's going to be important to remember that UVC energy damages materials, and the same is true for the materials that make up the LED device in the package, which is one of the reasons why the reliability of UVC LEDs is problematic. Those high energy photons coming out of UVC LEDs damage materials in the LED material itself and in the packaging material, and it's going to be a consistent problem for UVC LEDs. Finally, I want to discuss Excimer UV sources, as there are a lot of excitement around UVC Excimer sources, especially recently with the onset of the pandemic. Now, Excimer lamps have been around for a reasonably long time. You can even purchase Excimer lasers, and this technology has been used in semiconductor manufacturing for well over 30 years. Of particular interest in the germicidal world is a particular Excimer lamp that uses the gases of krypton and chlorine. Krypton chlorine forms a particular Excimer lamp, and like all Excimers, they typically emit at a relatively narrow wavelength. Now, in terms of design, an Excimer lamp is a lot like the design of a mercury lamp, except it contains no mercury, and the specific operating voltages are a little bit different as well. Specific gas combinations are known to form chemical compounds that are called Excimers. That's where the name comes from. And the krypton chloride Excimer emits at 222 nanometers, which some people call far UVC. Of course, 222 nanometer UVC radiation will be germicidal, and it will kill virus, and it will kill bacteria. Unfortunately, we'll be stuck with the Excimer lamps for some time. In my opinion, UVC LEDs operating at these shorter 222 nanometer wavelengths with useful efficiency and lifetimes will be very, very hard to make. And in my opinion, may never get to practical levels of performance or reliability for germicidal applications. I know the companies are trying to do it right now. There are some very low power 232 nanometer 230 nanometer LEDs that have been made over in Europe. A US company is looking at making them as well, but it's a very, very tough problem. So I'm afraid we'll be stuck with tubes and Excimer lamps for the foreseeable future. Now, one thing before I continue from this slide about Excimers is, and I don't have a slide to discuss it, is that in order to measure dose, the all-important dose that is required to determine whether or not you will have enough UVC radiation to disinfect microbes and viruses, you'll need a good UVC radiometer. And that said, UVC radiometers are really quite specialized. They're not like regular photometers that you use in general lighting, because there are no really good UVC sensors. It's possible to make new kinds of UVC sensors, but right now we're stuck with silicon photodiodes, and they don't measure UVC very well. So UVC radiation sensors tend to be quite expensive, and they frequently require recalibration. Also, they're very specific to given wavelengths that you want to be able to measure in the UVC. Finally, even when a UVC dosimeter can claim to be cosine corrected, frequently it's not very good at measuring UVC radiation coming in from the sides. And it's possible to get wildly varying doses from different kinds of UVC radiometers. So just keep that in mind if you're going to start taking a look at certifying UVC sources for germicidal applications. You have to be very careful about measuring the dose properly. Now, in my final slide, I just want to show where some UV systems have typically been used in room disinfection, actually since the 1950s. What you see here on this slide is probably one of the earliest applications of UV germicidal disinfection in the built environment. Now, remember we've talked about how UVC radiation can break DNA molecules, how it can damage other kinds of organic materials in the built environment like polymers and paints and fabrics. Similarly, it can be damaging to human skin and eyes. And as a result, it's typically agreed that if you use UVC radiation, you need to keep it away from people. And that's typically why UVC systems are used to illuminate ductwork, in some cases to purify air going into rooms. It's also used to disinfect the upper air inside of a room where specialized optics or reflectors are used to shine UVC radiation back and forth above where people are for disinfecting air in different spaces. But you don't want to really shine UVC radiation on people at all. Now, this is where the far UVC at 222 nanometers is gaining attention, because at this particular wavelength, studies are showing now that it may in fact be skin safe and eye safe, because at that wavelength, the radiation does not penetrate the dead skin cells in your tissue, and it doesn't penetrate the surface layers of moisture and cells in the cornea. But these studies are ongoing. Most of them have not been done on humans, although there are some human studies that have been published recently. And more importantly, the long-term impact of 222 nanometer radiation on people and materials in the built environment has not been studied. So it's going to take some time to really figure out how safe 222 nanometer radiation is for building into full-time disinfection in the built environment where people are present. So to wrap up, UVC is a potent germicidal technology. It always kills if the radiation can reach any form of the pathogen at the right dose. It's been around a long time, and new technologies like LED and Excimer lamps will continue to push the germicidal field forward. What we need is more research. And since I'm a research professor, I always like to say that. But regardless, we need to really understand what the impact of long-term UVC exposure is going to be in the built environment on both people as well as building materials. And in my opinion, we've much more to learn. Now, I'd like to turn it over to Dave for the manufacturer's view.
Great. Thank you, Bob. First, I also want to thank the IALD for conceiving and organizing this session, and for inviting me to participate. And thank you, Bob, for that excellent overview and update. Needless to say, from a product innovation and development side, we've had to do a tremendous amount of research to come up to speed on GUV technologies, along with everyone else. and it's taken a fair amount of diligence to sort through the noise to discern what is real information and what is misinformation, so we can answer the many questions being asked by designers, customers, and other stakeholders in the market. One of the things, before I start the slides, one of the things that may warrant clarification up front is that COVID-19 is not a virus. COVID-19 is a disease in humans caused by a coronavirus that appeared in 2019, hence the term COVID-19 or coronavirus disease 2019. The actual name of the COVID-19 virus is SARS-CoV-2, which distinguishes it from another well-known coronavirus named SARS-CoV or SARS-CoV-1, which appeared in 2002 and was responsible for the severe acute respiratory syndrome or SARS outbreak. With that being said, we've also had to deal with the fact that while the science of GUV in general is well established and well documented, research and applications with respect to COVID-19 and the SARS-CoV-2 virus have been slow to emerge. Nevertheless, there is now a confluence of published and unpublished information that allows designs to move forward with reasonable certainty. Still, the first question many designers are asking is, how do we know it will work? And that's an understandable question, considering that we are used to flipping a switch and seeing a lighting effect. But with UVC, we cannot see what's happening. In fact, if the source output is truly limited to UVC radiation, you can't even tell that the source is on. But of course it will work, because Bob told us so when he said, if a high enough dose is delivered to the DNA or RNA, UVC radiation will kill all pathogens. All kidding aside, it is in fact true. And as for COVID-19, we are talking about a coronavirus, an enveloped, positive-sensed, single-stranded RNA virus nearly identical to the better-known SARS-CoV-1 virus. Early predictions based on genome suggested that there is less than a 1.5% difference in the UVC susceptibility between SARS-CoV-2 and SARS-CoV-1, and subsequent findings are confirming a close correlation. Even so, we are also being asked, can you prove that your product will deactivate the SARS-CoV-2 virus? I have no doubt that we can, but it is fundamentally unnecessary for GUV products to be tested against a single pathogen, especially SARS-CoV-2, for reasons I'll explain in a moment. Also, due to current restrictions on the handling of SARS-CoV-2 virus, such testing can only be administered by a biosafety 3 or 4 facility. And needless to say, these labs are quite busy with other matters at the moment, as they should be. Frankly, proof that a UVC lamp or product can deactivate SARS-CoV-2 is, as one expert put it, quite uneventful, especially when we consider what we might expect a GUV system to accomplish overall. And that the emerging data suggests that it's easier to deactivate SARS-CoV-2 than other well-known viruses of concern. This suggests that other viruses, such as MS2, probably represent a better benchmark for disinfection than the deactivation of SARS-CoV-2. What is necessary for product assessment and application is much the same as you would require to execute a lighting design. A verified UV spectral characterization or UV spectral radiant flux report, and a corresponding UV radiant intensity report, which typically consists of a polar plot and a database of intensity values in an IES format, where intensity is reported in milliwatts per steradian. Together, like the spectral power distribution and photometric reports associated with luminaires, these provide the basis for GUV design. The UV spectral radiant flux report will confirm that the unit does produce UVC, which tells us that it is capable of deactivating the virus, how much of the energy is delivered in the UVC range, and what the peak wavelength is. And like a photometric report, the UV radiant intensity report will tell you the intensity distribution, so you can calculate the irradiance delivered to specific points much as you would calculate foot candles or lux. However, standard lighting design software typically only works with candela values and lumens, which are related to the sensitivity of the human eye, and they won't work with irradiance power data. AGI is working on a version for radiant power, but it's not yet available. So chances are you will need to use a different calculation software. There are a few available that work using radiant power data, or you might need to rely on your manufacturer for calculations, at least for now. The bigger question for designers, though, it's going to be, what dose are you designing to? And like designing a lighting system to meet lighting requirements of a given visual task in an environment with given reflectance values, etc., the UV dose does depend on the task and the situation. Specifically, dose depends on the pathogen, the level of disinfection desired, the UV wavelengths delivered, and certain specific project characteristics. Level of disinfection is typically described in terms of a reduction in the number of viable viruses, bacteria, spores, or what have you, after a dose of UVC is administered. Referring to the table on the left, a reduction factor of 10, with 1 out of 10 microbes remaining infectious, is considered a 1 log kill. Likewise, the point at which only 1 in 100 remain viable is considered a 2 log kill, and so on. The 5 charts on the right are from a study of 5 waterborne pathogens treated using a variety of UVC LEDs and germicidal mercury lamps. If I highlight the data collected using just one of those sources, we can see that the dose required to achieve a 3 log kill varies significantly from pathogen to pathogen. In this case, there is nearly a 23-fold difference between the lowest required dose and the greatest. So target pathogen does matter. Also, note from the chart that no level of disinfection eliminates everything. In all cases, there will be some portion of viable pathogen remaining. UVC systems do not kill and deactivate every instance of the virus or the pathogen. GUV should not be referred to as sterilization, and you should not guarantee that your designs completely eliminate the threat. Chances are that GUV is only one of the disinfection countermeasures implemented on a project. It's a good one, but it's not the end all. Now, what about wavelength? Here again, we see the effects of various UV wavelengths and combinations of UV wavelengths on bacteria in water. This shows that the dose for achieving a 3 log kill ranges from 8.5 millijoules per square centimeter to 17.5 millijoules per square centimeter. Curiously, it also shows that when longer wavelengths are present, a 3 log kill is not achievable. This is due to a process called photoreactivation, whereby some pathogens can use longer UV wavelengths and visible light to repair themselves and become reinfectious. By and large, viruses perhaps present the greatest concern, and they are characterized by action curves that closely follow the germicidal action spectra of DNA, such that an effective dose for any given peak wavelength can be deduced from the data derived using another peak wavelength. For example, here we see the relative intensity of the germicidal low-pressure mercury lamp, shown in green, and that of a UV LED with a peak wavelength of 275, shown in blue, plotted against the germicidal action curve for DNA as derived from the irradiation of the MS2 virus, shown in brown. As you can see, the effectiveness of these two UVC sources are comparable, such that a known effective dose for a low-pressure mercury GUV system will also apply to a solution based on 275 nanometer LEDs. This also tells us that systems with peak intensity between 254 and 275 nanometers are more effective and can achieve similar levels of disinfection using a lower dose, while systems that deliver peak intensity above 275 nanometers and below 254 nanometers down to about 230 are less effective and will require a higher dose to achieve comparable levels of disinfection. We also know that some pathogens become more resistant to UVC radiation when they associate themselves with surfaces and water. And this can affect the dose required to reach a given level of disinfection. Generally speaking, surface-borne pathogens require a higher dose than airborne pathogens. Waterborne pathogens require a higher dose than surface-borne pathogens. And for surface and air disinfection, doses must be increased as humidity increases in order to achieve comparable results. For example, here's a plot showing the dose response of surface-borne MS2 virus at 55% relative humidity, 85% relative humidity, and in water. Looking at the data points I've circled, we can see that a 10 millijoule per square centimeter dose of 254 nanometer UV will deactivate nearly 99.999% of the virus on surfaces at 55% relative humidity, but less than 99.99% at 85% relative humidity, and less than 90% of the virus when it's in water. If you're inclined to delve into research reports to ascertain what dose might be appropriate for a given pathogen and level of disinfection, be sure to note the wavelengths used in the study and whether the study relates to airborne pathogens, high or low humidity conditions, surface disinfection, or deactivating pathogens in solution, so you can assess if and how the findings relate to your application. Otherwise, again, you might need to lean on your manufacturer for guidance. Knowledgeable manufacturers can provide some guidance for establishing a target dose, but ultimately, it is the customer who must decide what they want the system to accomplish. For surface disinfection, you can calculate the irradiance on a surface, and as Bob explained, multiply the irradiance by time to determine the resulting dose. Bob expressed the irradiance in watts per square meter and dose as joules per square meter, but these values can also be expressed in milliwatts per square centimeter and millijoules per square centimeter. Of course, it's also true that you can take the required dose and divide by the irradiance to calculate exposure duration required. So for example, if the required dose is 10 millijoules per square centimeter and the calculated UVC irradiance is 0.003 milliwatts per square centimeter, then the dose will be achieved after 56 minutes of exposure. And by the way, dose is cumulative, so it doesn't all have to happen at once. 2 separate exposures of 28 minutes each will achieve the required dose as well. As for upper room air GUV systems, there are a couple of ways to approach the design. These include an evidence-based volumetric method that equates levels of UVC in the upper portion of the room to swapping out the air in the room for cleansed or fresh air. For example, a typical hospital isolation room might have a requirement of 12 air changes per hour. However, a typical office or school HVAC system may not be designed to perform that many air changes, and using the HVAC systems to treat and exchange the air does not disinfect between occupants as air circulates within the room. Studies have found that delivering 13 to 17 milliwatts of UVC radiation into the upper air of the room for every cubic meter of room air has the same effect as 16 to 24 air changes per hour and can reduce the transmission of pathogens in the room by approximately 80%. So this becomes a fairly easy calculation. Based on the total UVC output wattage from the manufacturer's radiometric test report and the total room volume, you can determine the number of units required and arrange them for uniform coverage to achieve the equivalent of a room designed for infectious control while using fairly standard rates of air circulation. For example, a room with a volume of 225 cubic meters requires 3,825 milliwatts of UVC for effective upper room air disinfection. Using a fixture that delivers 480 milliwatts of UVC then requires that 8 fixtures be installed. Finally, I'll say a few words about controls. Controls are certainly required to prevent human exposure to UVC. Controls may be integral to the equipment or implemented via building management systems or both. As with lighting systems, controls are required to limit energy consumption and to limit operation to only the minutes or hours required for disinfection. So exposure of furnishings and finishes are also minimized. Controls are also useful for making future adjustments to compensate for the diminishing output of UVC sources over time, and or to address variable demands for disinfection, either seasonally or as concerns about known and or new pathogens rise and fall. Thanks for your attention. I hope this helps, and I'm going to let Darcy here take it from here and bring us home.
Thanks, Dave. So as we transition to a designer's perspective, I think it's important that we understand a bit more of the history of UV, specifically for disinfection, so we can really understand the context under which much of the existing technology was developed. Infection control in general can be thought of as a concerted effort to reduce pathogens in our environment. In today's COVID climate, we're often seeing infection control focused around disinfection of surfaces, everything from handrails to PPE. But many of the applications of UV have been based on other specific ways of applying UV that have been developed, tested, and used for over a century. So where are we likely to already see UV in use? The first known use of UV is for water disinfection, and that application dates back over 100 years, making it the most established use of this technology for killing pathogens. Upper air GUV, as Bob and Dave touched on, was really first deployed in the 1950s in hospital settings and was quite effective. But we saw it phase out around the 1950s, but we saw it phase out around the 1970s as effective antibiotics became cheaper and more widely available. And finally, another tried and true application to note is integrating UVC lights into HVAC units to treat the air as it is being conditioned. We see this application typically as UVC sources integrated at the cooling coils to help sterilize the air, with the added benefit of reducing buildup of bacteria and mold on those coils. So UV for disinfection is clearly not a new application, but in today's COVID climate, we're seeing UV touted as an option for helping to speed up our return to school, work, and the rest of pre-pandemic life. And lighting designers are often getting asked, how do I do UV lighting, even though we know it's not really light? As a design community, we're finding ourselves to be the resource for our clients who are trying to get a grasp on this technology. What is it? What does it take to do? What do I need to be careful of? And basically, how do I do this? So before leaping headlong into a UV application, there are two fundamental questions that a designer needs to ask that will help guide the application of UV. First, what type of pathogen needs to be controlled? And second, what actually needs to be disinfected? So first, a designer needs to consider the various types of UV sources that are available and exactly what they're capable of doing. UVV, which you'll often hear as purple or indigo lighting or just by 405, is extremely effective against bacteria. As Bob talked about earlier, it causes the creation of reactive oxygen species within the bacteria cells, essentially causing the bacterium to bleach itself from inside. 405 is also effective against a range of molds, fungi, and yeast. When it comes to viruses, though, the data that we're most familiar with shows only two limited viruses against which 405 is effective. In general, 405 is not considered an antiviral agent. Next, UVC. UVC is our more traditional source, usually just referred to as 254. UVC is extremely effective at killing bacteria and fungi and in activating various types of viruses. Not only is UVC effective at inactivating a huge range of viruses, such as neurovirus, influenzas, polio, etc., but recent published research has indeed confirmed that 254 does inactivate SARS-CoV-2, the virus responsible for the current COVID-19 pandemic. FAR UVC, specifically 222 UVC, is emerging as a very promising new technology for disinfection. It has many of the same properties as traditional 254 UVC. It's great at killing bacteria and mold. It can inactivate viruses. It fundamentally works the same as 254 UVC by disrupting the DNA or RNA directly. But the reason that it seems so promising in application is that only the longer UVC wavelengths actually penetrate the skin and corneal cells to cause damage. The shorter FAR UVC wavelengths are too short to be able to penetrate the outermost layers of our skin and eyes. And while it is expected to be effective against SARS-CoV-2, conclusive data has not yet been published. So while it's important for us to understand the various types of UV and what they're effective against, it's also critical to understand how those types of UV can be used safely. The table here presents those same three types of UV just discussed, 405, 254, and 222. So knowing what type of pathogen we're trying to control and what types of UV are effective against it, we can start to ask how we can use those sources. In general, 405 is considered safe for use in occupied spaces. It's often integrated with typical white light electric lighting for full-time disinfection, then can be ramped up when the space is unoccupied to increase dosing levels. Because it's generally safe, it doesn't really need to be relegated to self-contained or shielded units. On the other hand, 254 traditional UVC sources, which are much more broadly effective than 405, can cause harm to occupants of the space. As such, you'll often see 254 used in self-contained units like disinfecting cabinets. Or 254 might be integrated into those upper air GUV fixtures where they are completely indirect and shielded from view. 254 should not be used in occupied spaces though, so the integration of safety mechanisms are critical. The safety mechanisms can include occupancy sensors to make sure the lights turn off if someone is nearby, or red indicator lights to let you know the unit is working since we can't see UV, or adding the blue glow so the fixtures appear on, or integrating lockout control mechanisms that keep people from entering the room, or so on and so forth. Finally, the newer 222 technology, as I said, is very promising. The preliminary studies are showing that it is safe to be used in occupied spaces because it essentially can't penetrate the outer layer of our skin and eyes. That makes it suitable for use in occupied and unoccupied spaces, in direct and indirect applications, because it doesn't carry the same risk as traditional 254, but has many of the same germicidal properties. So now that we've talked about the types of pathogens, viruses or bacteria or fungi, that we want to get rid of, how the types of UV interacts with those pathogens, and some of the safety risks, the next step is to really understand where those pathogens might be. Basically asking ourselves, what are we trying to disinfect? So starting at the top, water. As we talked about before, water treatment is a tried and true application for traditional 254 UVC. Typically, this is achieved with submerged UVC sources in water that has been filtered to improve clarity. What about the air? If we're trying to control outbreaks of diseases like COVID-19 or measles or any number of other airborne pathogens, killing or inactivating the pathogens by treating the air is critical. And there are a number of ways this can be achieved. As we talked about before, upper air GUV, which is using indirect UVC fixtures to create a killing zone through which the air in a space is circulated, is a time-tested and proven method for reducing airborne transmission, but does require high airflow rates. Similarly, as we talked about above, integration of UVC into HVAC units is also an effective way of sterilizing the air and keeps the UVC source away from occupants. Additionally, there are products on the market, a market that is definitely growing right now, that integrate UVC sources into ceiling fans, for example, so you really get good airflow to allow for circulation of that sterilized air. There are also portable air purifying cabinets. Think your typical home or office standalone air purifier, but with a shielded UVC source. These options are handy because they don't require electrical or architectural infrastructure, but the radius of effectiveness is pretty limited. In other words, they really don't work well in large spaces. What about the surfaces in a room? Pathogens like MRSA, which is an antibiotic-resistant bacteria, are typically transmitted via contact with infected surfaces. So disinfecting surfaces is a very critical part of controlling that pathogen spread. In general, there are two broad approaches to disinfecting surfaces in a room, either permanently installed direct fixtures that shine UV onto the room surfaces, either when occupied in the case of 405 or 222, or when unoccupied for 254. There are also mobile UV fixtures, UVC robots, for example, that you'll often see used in clinical settings. These robots move around the room so they get line of sight to as many surfaces as possible, since UVC is essentially effective only via line of sight. Basically, there is no inner reflection. And finally, what about the parts of our spaces that move? Objects like cell phones or computer keyboards or any number of things which are generally gross because they get touched a lot but may not be fixed in place. The solution we're often seeing for those, which is more or less a non-lighting solution, is sterilizing cabinets that you put a device in to be cleaned with UV. These types of applications are all pretty standard. We are seeing a rush to market from manufacturers of all stripes to provide UV fixtures with new form factors and integration though, so let's touch on those. Some of these promising emerging applications for UV are essentially bringing those more traditional applications into new spaces. As we talked about, upper air GUV is a time-tested, tried-and-true method for air disinfection, but historically it's been relegated to clinical settings like operating rooms or congregate settings like homeless shelters. Many of the discussions recently have been about other applications where upper air GUV would be a great fit. Places like gyms, where you typically have higher amount of air circulating in the space to keep people cool and reduce odors, are already primed for upper air GUV. Places like airports or arenas with large congregations of people could also use upper air GUV as a method for controlling the risk of terror attack via microorganism, things like the use of weaponized anthrax. Secondly, we're seeing full-time disinfection using 405 moving out of the clinical settings where it's generally been relegated. Now the discussion is about integrating 405 into all sorts of non-clinical settings like office spaces or schools. Third, the emergence of 222 or far UVC as a full-time disinfection source in all sorts of spaces is a very promising application. And finally, we're seeing a very quick rush to market with devices that bring that 222 down closer to the surface it's disinfecting. Things like portals or wands that can provide a higher dosing level by being closer to the object they're disinfecting. But with this rush to market, there are some important safety issues to keep in mind. The Underwriters Laboratory has published a fantastic guide that helps users understand the types of UVC applications in particular and their safety regulations or safety concerns. Keep in mind this is all specific to traditional 254 UVC sources. Another thing to note is that UL is essentially looking at these devices from an electrical safety standard point of view and defers to other authorities as to the photobiological safety of them. The first two rows shown here, the home use personal UVC sterilizer and UVC wands, are an interesting piece. UL is essentially unwilling to certify those devices for safety because they don't contain the UVC and typically don't have enough in the way of safeguards. I don't know about you, but my social media targeted ads have been full of these types of devices, which is concerning to say the least. The second two rows shown here are the applications we've talked about above, self-contained UVC sources that clean the air or clean devices that get put inside. This slide continues the table, which contains a few more types of devices beyond what I'm sharing with you today. You can see all the types of applications we've discussed so far: upper air GUV, UVC robots, UVC integration into HVAC, and hybrid systems, all listed here. I won't dwell on this too long. Please check out UL's document for more in-depth information. But the important takeaway here is that the regulation of this market is about two things: electrical safety and photobiological safety. It is really important to note that neither of those address biological effectiveness. But as we start to stretch the broad scale application of UV to many more parts of our built environment, we as designers have some critical questions to ask. First, how do we as designers calculate UV applications so we know how many fixtures to use, at what spacing, and at what height? UV output of a fixture is not captured in photometric reports for obvious reasons, as Dave talked about, so it's a whole new data set. And when you bring in the issue of surface reflection really isn't well known or quantified for UV, how do we effectively calculate our applications? Second, how can the installation be validated? I assume I'll need to buy a UV meter. Where are those available, and how much are they going to cost us to purchase and keep calibrated, since they need to be calibrated for specific wavelengths? Third, if the owner of a space is going to maintain the system, there are a lot of questions to ask. Do they have access to a UV meter to validate that the system is working since you can't see it? Or do they have the ability to make sure that the levels of UV that are provided are within the dosing limits? Fourth, the life rating of many UV sources are short compared to the world of white light LEDs. Are owners understanding their life cycle costs? What happens at the end of life? Is there an end of life mechanism that shuts the fixtures off when they've depreciated to a level that they wouldn't be effective? How does the owner know that it's burnt out prematurely? Fifth, what control mechanisms are built in for safety? I've seen UVC robots hit the market with directional occupancy sensors that only look one way, despite the product having a spherical distribution. Sixth, and this is a big, fat, hairy, loaded question: what is my liability as a designer if someone is overexposed? What about my liability if the system isn't strong enough and someone gets sick? What about the liability on the owner for maintenance, or the calculation software manufacturer for accuracy, or the fixture manufacturer for rated life? This is a big question that isn't going to be answered today. Seventh, what really is the long-term exposure risk for 405 or 222 applications? The studies that are recent or ongoing are showing them to be safe, but have they really been used long enough for us to really be confident? And last, how do these systems fit within energy codes? If I'm using a downlight with integral full-time 222 disinfection, and there's one UL label that indicates the combined power consumption, does the whole fixture power need to comply with my energy code? Or do we have two different electrical systems in one fixture? And even bigger questions than that, we have some additional things to consider. UV sterilization should always be secondary or tertiary cleaning protocols. The CDC recommendations should always be followed first. Specific to 405 applications, as lighting designers, we should be considering the impact on the visual environment. The introduction of 405 for full-time disinfection will add a purplish tint to the light, reducing CRI and shifting the CCT. Is that acceptable? Does it feel good? I'm not sure we have an overall answer to that, other than that it depends on the specific application. As Bob mentioned previously, one really big factor to consider in the mass deployment of UVC sources, in particular 254 and 222 options, is the degradation of materials in a space. If we're going to use, for example, full-time 222 downlights to control pathogens, we need to make sure that the owner is aware of the fact that their carpet is going to degrade faster than expected, and the impact of that degradation on their ongoing maintenance costs isn't small. What about the long-term impact on our microbiome? Our environment is filled with all sorts of good bugs. Our bodies are covered and full of good bugs. It is a more philosophical question, but it is rooted in science. What are the long-term consequences of living in a more sterilized world? Does it ultimately make us more susceptible to this next bug? And for those of us who work in the transportation world, we often hear the term security theater. It's the in-your-face showing of security measures that makes us all feel safer. We're seeing that in today's climate with cleaning, what's been termed hygiene theater. This takes many forms, having the cleaning crew come to clean your office space during the day instead of after hours so people actually see door handles being wiped down, for example. Some of these more visible options where we see a fixture or see a device or see a different quality of light might be another set of tools to help people feel more comfortable to speed up our back to normal push. So I'm thrilled you all could join us today because we as the lighting design community are really focused on three main things: educating our clients so they can educate theirs, following the current research, which honestly seems to get updated almost daily, and finally learning about the different types of products and applications that have been traditionally used and what is rapidly emerging. With that, I'll wrap up and thank you for your time.
All right, we do have some questions. I know we're tight on time, but we're going to try to answer one or two. I know, Darcy, you had a question for the other two speakers while I get some questions put together.
I did, absolutely. Yeah, I think one of the questions that we have asked ourselves and that we've had conversations with our clients about is how long do we really think this technology, this discussion about UVC is going to dominate our day-to-day discussions? Like we saw in the 1950s, this technology really took off and then kind of went by the wayside when antibiotics got cheap and easily available. Do you think that given the scale of today's pandemic, this technology is likely to persist, or do you think we're likely to see it kind of fall by the wayside? And Dave, I'd ask you probably here first.
Oh, sure. Yeah, that's a great question, especially since we know that many upper room air disinfection installations were removed once we became more complacent with antibiotics and so forth. However, I think this pandemic has created a much higher awareness than we've ever had. And that an awareness that we're never really immune from this kind of a threat, and that this can and probably will happen again. So I think this time's a little different. I think these technologies and practices are going to remain relevant for quite some time. I think eventually we'll settle into some acceptable design guidelines and practices at the least, but I think we're just going to raise the defense level somewhat, so it's just not so bad next time. You know, we've got something in our, built in. And I think that's worthwhile. I don't know,
Bob, what
Bob,
about you?
Yeah, I tend to agree with Dave. I think that the time constant of the fear of COVID is going to leave UVC disinfection more current for a while. But it's kind of a crystal ball question. It's really going to depend upon the perception of the individual clients, as well as a better measure of the collateral damage of UVC, energy damage, materials damage, risks of human exposure, and so on. There's so little that we know about some of these kinds of systems in real operation. So it's going to be a really interesting learning curve. And but I think we all hope that a vaccine comes very soon and we won't have to worry about it.
Very true. All right. First question, will the slides be available for distribution to the attendees? If there is no answer yet, you need to talk offline, we'll talk off that, but will they be available to the attendees?
I think the IALD would make that available.
Okay.
Or not.
I'll check.
I would contact the IALD if you're interested in that.
You can always watch the watch the rebroadcast of this. We'll have it up on our YouTube in a few days or so.
Or contact either one of any of us.
Yeah. Again, I want to be mindful of everyone's time. Thank you so much for all these questions. We'll find a way to get back to you, but I do want to ask 2 questions. First, let's go to Bob. We have been asked by our customers whether any of the UVC lighting is certified by the CDC or the FDA to kill COVID-19. Do you know if any have been certified?
To the best of my knowledge, at the present time, the FDA has not issued any emergency use authorizations for UVC for pandemic management. I know of at least 5 or 6 companies that have filed emergency use authorizations for UVC radiation, but to the best of my knowledge, none have been issued. I think this is going to be kind of interesting to see. Having said this, the CDC has written pieces about the effectiveness of UVC radiation for disinfecting personal protective equipment, particularly N95 masks, and it can be recommended, but there's no emerging consensus that the FDA is going to issue approvals.
Okay, next question and final question. We'll start with Darcy, and then Darcy pass it over to Dave. And you kind of touched on this, but I want to hear a little bit more about this. Are all these LED wands and boxes of any value? Our impression is you would need to hold it over the target for a very long time to have any effect.
Yeah, I would say that I'll leave it to the others to really talk about effectiveness. I'm concerned about safety. So the wands, for example, many of them have a shut-off mechanism, so they shut off when you tip them above 90 degrees above nadir, with the idea that they're going to protect your eyes. That doesn't take into account that my dog or my toddler might be standing right next to me when I'm using these devices, and it's part of the reason that UL is essentially not certifying them. The other home marketed device we're really seeing is these standalone broadcast UVC sources that shine light in all directions. I'm actually seeing some that advertise that they make ozone. Well, ozone's a biohazard if in a contained space. And so the idea that they're actually selling these products with the explicit intent of making ozone to clean the air is scary, because to me they're not accurately representing some of the safety concerns. And the fact that it can't get a UL or some other kind of electrical safety rating on there helps indicate that. Dave, transfer it off to you for your thoughts.
Yeah, really, by and large, I've dismissed them, partially because you have to have a very specific instructions in terms of, in other words, what are you trying to do? What is the dose you're trying to get to? And distance and power is going to have everything to do whether you get that dose or not. So it's, they may say you have to put it a certain distance above something and hold it there for a certain amount of time, but it's so unreliable and so subject to misuse that it's not worth considering in my mind.
And I agree with Darcy and Dave. I don't think that they're worth the investment, too dangerous to use and of limited effectiveness, probably capable of being misused fairly easily. As an LED guy, I say that's where bad LEDs go to die. But that's just my particular position.
All right, thank you. I did get an answer about the slides, and yes, attendees will be sent slides, so we'll send a link out for that. Thank you, everyone. Thank you to our speakers. Thank you to our attendees for taking the time. I know everyone's time is important. Thank you for sticking around. We once again want to thank our sponsor, the Lighting Quotient, for supporting this webinar. Thanks, everyone, and have a great rest of the day.
Thank you.